But when we think about arterioles, arterioles are different. Arterioles are going to regulate within the organ. So we think of this as local control. So remember that these are smaller than arteries. We have less smooth muscle, and we're distributing now within the organ. So this is now a, oh, I'm right. Local control. Do I want it to go to this piece of muscle? Do I want it to go to that piece of muscle? Do I want to go to this region or that region? But it's within the organ, not whole body now, but locally. And so the radius has the biggest influence because the heart's going to be putting out whatever pressure it's got. We're certainly not changing the length of the viscosity. So minor changes in the radius will have huge changes in blood flow. And what we do to do this locally is we use paracrines. Remember paracrines? We said that they were a small chemical communicator that travels from cell to cell within the extracellular fluid. It doesn't go through the blood. It's not a neurotransmitter. It's cell here talking to cell there, and we use a paracrine. It's through the ECF. And we're going to communicate with these nearby cells. And this is how we regulate blood flow in arterioles. So there's 4 basic types of regulation. We have active hyperemia, which I talked about in lab, and reactive hyperemia, autoflow regulation, and myogenic tone. So let's start with active hyperemia. And I drew it on the board as just words, but I found this picture in your book, which I thought was interesting. So the key with active hyperemia, it's an increase in the activity of the tissue. We're creating metabolites. We're being more active. And some of it's about the carbon dioxide and the oxygen. I also mentioned that hydrogen was part of it. ADP is part of it, and other metabolites. These all act as paracrines in this active tissue. So these cells are telling this arteriole, we need more blood flow. And so we get vasodilation. And so you can see this is slightly larger. So we have vasodilation so that we can have this greater amount of diffusion, and these cells will get fed what they need to support their activity. Now, a lot of times we think about this in terms of muscles being active, but it can also be part of your brain being active, part of your digestive system being active. We open it up so that the activity is supported. And it shows here that if it keeps going, then over time, we have the greater diffusion that feeds the cell as needed, and we continue to have vasodilation. If the activity discontinues, these paracrines, these metabolites disappear, and without any nerves, the smooth muscle just goes back to its resting state. It doesn't need, it will constrict on its own without anything else. The vasodilation goes back to normal. The key is that this is all based on metabolites, oxygen, CO2, hydrogen, everything else, and we call these paracrines. Okay. I wanted to stress again, like I did in class, active hyperemia is normal and healthy and what we want to happen, because it means that the body is feeding cells that are working, and that's what we want to have happen. However, reactive hyperemia is taking that same system and responding to a non-normal situation. So if I have a constriction, we call it ischemia. We have a lack of blood flow, right? So if I have a decrease in blood flow, I will get a buildup of metabolites. And the paracrines are the same, and we get the same effect of dilation. It is the cause that is different. And in class, I gave the example of the string around your finger, or a tourniquet, or a blood clot. Anything that prevents blood flow will cause reactive hyperemia. And this chart is from the your book, you can follow it through. But the key is when the blood flow goes down, we get all these things and we get the vasodilation. Here, when the active hyperemia, it's all about metabolic rate causes vasodilation. So in both cases, we get vasodilation. Both cases, we get an increase in blood flow. It's the cause that is different, okay? That's the thing. So the thing about reactive hyperemia is if you dilate the blood vessels and you let blood come back all at once, we can get something called a reperfusion injury. The blood flow is returning to the area so quickly that too much blood fills the area. We'll get swelling, we'll get edema. And again, I give the example of the string around your finger. When you took it off, your finger turned bright pink. Tourniquets will do this as well. So what is myogenic tone? Myogenic tone is in the muscle, myo. Remember, myo means muscle. It's based on the stretch of the muscle fibers within the arteriole. So if I stretch them because I have more blood flow coming in, maybe I started exercising, more blood flow, but this area doesn't need it. So if you're going to go exercise, we increase cardiac output, we stretch these arterioles, but your kidney says, I don't need extra. So these cells will actually have a vasoconstriction in response to the increase in blood flow to maintain a constant blood flow. But this is also probably related to the buildup or lack of buildup of metabolites. So if blood is flowing through faster, the metabolites wash away, we'll get some vasoconstriction. Now your book says it doesn't involve paracrines. Another part of the book says it may involve paracrines. They're not sure if it's part of the whole system or not. And autoflow regulation, there's a big debate. Is it real or is it a form of myogenic tone or active hyperemia? The key is that autoflow regulation is the name given to when we need to maintain constant blood flow. So it seems to be very related to myogenic tone. It just depends on what the overall blood flow is.